Hello, good day. Today we are going to see yet another simulation. This is called frequency responses. And before this frequency response, there were two other simulation procedures we have done using a finite element general purpose software. And the earlier simulation was model dynamics. And the model dynamics, we dealt with natural frequency, normal mode simulation, or fundamental frequency simulation. And in the fundamental frequency simulation, we found out the normal modes of the induced draft fan radial impeller. Now, we had found out the possible normal mode of the impeller, and we determined the frequencies that ranged from 250 Hertz to 350 Hertz. So this is called, these were called the fundamental frequency. These are called the fundamental frequency because there is no external load or boundary conditions imposed onto the impeller. So this is the impeller, and to the same impeller, the previous simulation what we performed was finding out the normal modes. So these were the normal modes. So we had 251, 318 and 330. These are the fundamental frequency. So completely the impeller is at rest, and only because of the internal atomic, the electronic spinning, okay, there are internal vibrations, and these vibrations are in these frequency zones. So 251, 318 and 330. And we said that these frequencies are very important, and identifying these frequency and comparing it with the operating frequency, we will be able to understand if there is a state of resonance existing, which means any of these frequencies from the normal mode, when equals to the frequency, that is the operating frequency, the frequency, then that is called to be the state of resonance. That is when the at that particular frequency the structure will fail. So that is what we concluded in the previous episode. And the episode before that, we dealt with structural simulation, where we applied the proper boundary conditions. We have also bolted the system, and we applied a rotational velocity at the center, assuming that there is a shaft which is rotating at about 800 rpm. And with this angular velocity, it exerted a certain force, that is the pressure force, the internal kinetic energy of the air, okay, from the shaft end, okay, is converted into pressure energy, and it is radially distributed from the exits. Okay, so that yielded a certain deformation and a stress, and the deformation was about 0.045 m, and then the stress values was was about 41 not mm. And we said that the structure seems to be stable and it is safer. However, just because these structures experienced a lot of vibration, we decided to go for a modal dynamics. We performed a normal mode simulation, extracted the three frequencies, and now we are going to get into frequency responses. So we need to understand how does the impeller behave when it is simultaneously introduced to certain external loads, and these external load is nothing but the rotational velocity itself. So when the rotational velocity is applied to the complete system impeller, what are the frequencies? So that is what we are going to find out. So now we are performing a dynamic frequency simulation. for that. So this particular model, it's the same 3D CAD model. Okay, and we are creating, I mean, we are giving a setup. So here you will find that this particular system, the setup, the dynamic frequency, which is the frequency response, it is linked to model 1. So model 1 is nothing but the model dynamics, the natural frequency analysis or the normal mode simulation what we perform. And it's linked, and whatever it's linked, the values are linked. So the normal mode values are 250, 318 and 330. So which means it is linked to it. And now what we are going to do is we are going to assume that there is a certain spring and damper existing. Okay, so now we have to very carefully understand what exactly is meant by a spring and a damper. So usually any vibration is going to be completely reduced, or the amplitudes of these particular vibrations are going to be reduced from a certain time t1 to tn, let's say. So from t0 the system is at rest, t1 the system started operating, so there is some small vibrations, so some amplitudes a1, and then time t is equal to 2 you get an amplitude a2, time t is equal to 3 you will get an amplitude a3, and at time t is equal to 4 seconds the amplitude changes, say about a5, sorry a4, a5, and what happens is now slowly the amplitudes will start coming down. So how the amplitudes are going to come down is there is going to be the stiffness induced by the material. The material itself will have a certain cushioning. So here in this case it is the MS plate, and these plates are welded together and it becomes an impeller. I mean this induced draft effect impeller. Okay, so in the preliminary simulation we discussed that the client's interest was into studying the actual differences between the casted product and the fabricated product. So this is supposed to be the impeller that you see here. It's an optimized impeller which we had designed, optimized. Okay, and this particular impeller is a fabricated impeller. So which means the plates are all properly stacked, okay, and it's bent into the shape and then finally welded. Okay. Now this welded structure is it's the final system, and this particular system, okay, being made of a certain material that has got a stiffness factor. Okay, so the stiffness parameter will be dealing with the geometry of the structure, how slender the members are. So here you will find the plates. Each plate is welded. These are the vertical blades, and these are the horizontal stiffeners, the top and the bottom stiffeners, and the central disc, and then the top shroud, and you find the top crown. So similarly you will also find the bottom shroud and the bottom crown. And now each member is designed uniquely and for a specific purpose, and that also we saw in the previous simulations. This is the crown which is made for taking the tension loads, so all those clearing stresses that comes on to the junction between the crown and the shroud will be taken care of. Okay, now there are going to be huge amount of pressure load induced onto the vertical member, that is the blade. Now this blade, okay, is the thickness of the blade is reduced so as to reduce the total weight, and as what we saw from the previous model simulation, we said that omega is equal to square root of k by m. Omega is nothing but the angular velocity, which is equal to square root of the stiffness divided by the mass. Now we have the overall mass here, which is almost 0.7 tons, and then the stiffness, and the material is mild steel, and that has got a stiffness. So everywhere you will find that the stiffness and stiffness is playing a main role. Okay, now what happens is the stiffness is going to create, I mean, that's going to contribute for the rigidity of the system. It is going to make the system or the model more rigid. Now, if it becomes more rigid, that is going to fail at some time. So what is needed is it needs a cushioning where that rigidity is reduced and it's tried to balanced with some flexibility. Okay, so instead of making it a completely rigid model, we are trying to make it a bit flexible. So there will be some dampening factor. So that is what here we see, that there is a damping ratio, and this is that damping factor, and we have a certain ratio that we follow, and here you find Rayleigh damping, and this is called as the modal damping. Okay, so this Rayleigh damping, that is again depending on the mass and the stiffness matrices that we discussed earlier. So the force matrix is equal to the stiffness matrix multiplied by the displacement matrix. Okay, so now from that we achieve that K value, the stiffness matrix we get, and the force matrix is nothing but it's a mass matrix multiplied by the acceleration due to gravity. So here this structure is going to be based on acceleration due to gravity g. So m into g is going to be k into x. So these factors, the Rayleigh factors, are introduced. And then we also have the modal damping, equivalent modal damping factors. So this is going to be the damper, and these dampers are going to reduce the vibration. It's going to provide the cushioning for that particular amplitudes. So the amplitude at time t is equal to 0 is A, then at time t is equal to 1 second it is going to be A1, at 2 seconds it's going to be A2, the third second it's going to be A3, so it will increase sinusoidally. Okay, and then at some point of time the amplitude is going to be very high, which means there is going to be an amplitude. Okay, the threshold is going to be very high, and it should not, be made that high, because the system has to be stable. Okay, or otherwise the system will become unstable and then it will go out of control. So there is a certain amount of damping which is created to this. So now these damping values, whatever we see here, these damping values are going to help us in deciding the bearings, the cushionings, and the system, the mechanisms that is going to hold, or the mechanism that is going to reduce the the vibrations, that is the extreme vibrations caused by the structure. Okay, so now we perform this particular simulation, and then what we need here is we need to have a function. We need to have a frequency function. Okay, so now this frequency function will decide how the amplitudes are going to be, whether it is going to be sinusoidal or whether it is going to be in a different pattern. Maybe you can say an S curve, or it is going to be discontinuous amplitudes, where you will have one set of amplitudes, okay, and then there is a gap, and then again there is an amplitude peak, so which means A1, A2, A3, A4, A5, A6, A7, that will be one, and then again the negative part of A7. So that is what you find here. At some point, the first point is going to be, the frequency is 5 Hz and the amplitude factor is 0.21. Okay, this is called as the amplitude factor. and we are deciding what will be the amplitude factors. So there are some places where the amplitude factors have gone beyond 2. Okay, so we can decide what will be the amplitude of those frequencies. So now based on this we are creating about some 30 points. So these are the functions. So now let's say how the function is going to be f of x. Okay, so this is the function, and how the frequency is going to vary with amplitude. So we have the x is equal to a cos omega t, and y we have a sin omega t, and omega is nothing but the angular velocity and a is nothing but the amplitude. So we get at point 1 what is going to be x and what is going to be y. Okay, so now based on this x and y, okay, there is a certain function, and this is the function, this is the curve function. Okay, and here you find that there are some sharp edge. The reason because we are taking only about some 30 points. Now if you try to make it about 100 points, you will find that these curves are going to be smooth. Okay, so this is almost equivalent to an excitation. This is called an excitation. So which means we are ticking on the impeller. We are going to tick on the impeller. Okay, why we are going to tick on the impeller is when there is a forced frequency. So that is what we mean by forced frequencies. In forced frequency, we ping that particular system with a fork, a tuning fork, and we try to apply some damping factor also. Okay, so one end you ping it with a tuning fork, and on the other end there is going to be a damping system. So that damping system can be a damper, a viscous damper. So viscous damper, like some kind of cushioning, neoprene cushioning, or maybe some damping materials, some fabrics. Okay, so here we are taking care of the damping with an external fabric or a material. The stiffness will be caused with some stiffness will be caused with will be considered by keeping some springs. That is, which means the system is going to be connected with some springs. Okay, and these springs, the infinital, see, we have to visualize it that way. There are infinite amount of springs which is connected on one side, and there is a infinite amount of damper connected on other side. So we have the central plate and the disc, and let's imagine that on the top portion of the disc we have the spring attached, and the bottom surface of the plate we have the dampers attached. So whatever stiffness is acting on the structure, okay, the corresponding, there will be a damping factor also below that. Okay, so that is going to dampen the system. So here there is an amplitude factor, and based on this amplitude we are creating a function. So this is the frequency function what we have given, and now what we do is we have to give an excitation. Okay, so that means there should be a load, an external load induced onto the structure. So this external load is nothing but the rotational velocity of say 800 rpm. So there is a inertia, a rotational inertia which we have given. So you will find omega here, and that is acting at the center of the impeller, and that's going to be about 1600 rpm. So now what we can do is we can reduce it. We will try to make it about 800, let's say 800 rpm, and then we are linking it with the frequency function. Okay, earlier we connected or linked it with the model simulation, what we did earlier with the normal mode simulation, and now we have given a function, a frequency function, and then we are linking it with the frequency function. Okay, so now what we do is we are going to run the simulation. And once we run the simulation, we will be able to get the displacement. So this is going to be the displacement. So here you will find that the displacement magnitude is 0.03 mm. So 0.03 is the deflection on this particular, the deformation on this particular impeller, induced draft fan impeller, radial impellers, when excited, okay, with an external loading. So there is a certain vibration caused, and we are giving it in the form of, we are giving an equivalent to damping and stiffening. Okay, so that is what we have given in the form of a pulse, and this pulse is the function f of x. Okay, so now we said that this particular function, the curve, whatever, or the amplitudes, whatever you saw there, that is going to be the pulse, and in that, you know, the rotation of 800 rpm is going to be of that magnitude. Okay, the excitation what we have given. So now that excitation is going to cause the system to deform this way. So this is the vibration that comes on the system. Okay, so now because of the vibration, because of that particular vibration of, you know, the rotational velocity of 800 rpm being excited with a pulse, with a response value, the frequency response value of the function. Okay, this is going to be the displacement. Okay, so now here you will find, yes, so this is how you will find how the vibration is going to happen on the impeller. So now this being a symmetrical structure, cyclic symmetrical structure, you will find, see, it's almost like, you know, you are trying to, you know, the from the center, since it is bolted to the shaft, it is trying to agitate this particular impeller in either direction. That is what you see here. This is how it's going to be agitated. And now you will find there is a torsion, and because of the torsion there are going to be a lot of stresses induced at the collar. So the junction between the shroud and the collar, this ground, is what we call as the collar, and the collar is going to experience a lot of stresses. If the crown wasn't there, the collar would have teared off. The reason simply because of the torsional issue. That means a torsional rigidity is going to exist at that particular portion, and then the system can tear off. Okay, so in order to avoid that from happening, what we have done is we have reinforced it with the collar, and this collar, this is what we call as the crown. Now let's see what is the stress values. So here it is the displacement value 0.03 mm, and now let's see what is the one measure stress value. So you will find the stress value is about 15.8. Yes, so still it is safer. Now when the rotational velocity of 800 rpm is applied onto the structure, okay, on a certain impulse dynamically, so there is a difference in applying a load statically and dynamically. Now the static simulation, the structural simulation what we saw in our first episode, is like applying that particular 800 rpm statically. The system, the entire system is going to have a static, which is considered to be a static system. Okay, and that static system is going to be given your rotational force, a rotational velocity. Okay, so which means it's bolted at the center, and these bolts are allowed to rotate. It's kept free along the axis, and what happens is when that 800 rpm is applied, the impeller rotates statically. There is absolutely no external disturbances at all. Now here in this frequency response, what we are doing is we are giving a pulse. Okay, and that is the the frequency response. That's the function what we are defining, and we are saying the 800 rpm is going to now be induced, or that is going to be enhanced with a pulse of what? Pulse of that particular function what we have defined. We have given certain amplitudes and then we have created a peak, I mean a curve, and that curve is the pulse. Okay, so now we have seen that the von Mises stress is about 15.8. So from this we infer that dynamically the system is going to be safer. So here you get the von Mises stress, and we are going to see what is the velocity, the magnitude of the velocity. So here it is about 0.04 meter per second, 0.04 meter per second, and how it's going to. So these are the velocity results. Okay, so these velocity, these are the contours, I mean the plots that we find out after the simulation. Okay, so this is the velocity plot, and now let's see what is the acceleration and its magnitude. So this is the acceleration, which is about 6970 meter per second square. Acceleration magnitude, the 70 meter per second square. So usually the acceleration due to gravity is about 9.8 meter per second square. Okay, so here there are some regions which is experiencing about 70 meter per second square. So 70 meter per second square is what? 9 multiplied by 9 is 81. 9 multiplied by 7, 7 9 are 63. So it is almost about 7.5 g. So 7.5 g is the kind of acceleration that is going to come on the system. Okay, so now what we do is we are going to perform a random vibration simulation after this, because we are experiencing an acceleration of 7.5 g here, and now we can understand that g is acceleration due to gravity. So the weight of the system is nothing but mass into acceleration due to gravity. Okay, so now the total weight what we have is about 0.7 tons. So 0.7 tons we can convert it into kg and we can find out, and now from that we will be able to find out what is going to be the acceleration. Okay, so now is this particular radial induced draft fan impeller weighing 0.7 tons capable of withstanding a 7.5 g force? That is what it means. So when I'll give you a small example about the cockpit of an aircraft. So whenever the electronic enclosures, the ECF, MC and ECU modules, electronic control units of the cockpit, whenever these modules are designed, they are going to be designed with a random vibration. They are going to experience certain thrust, inertia. So that can be about 1.5 g, 2 g, 3 g, 5 g, 10 g, 12 g. So it can go up to 15, 16 g's. Now what is going to happen when it is about 16 g? Whether the structure is going to wear out, because most of those enclosures are going to be fabricated systems, plates connected together, and they will be connected with the screws, and every vibration that comes onto the aircraft from the landing gear, okay, or even because of the turbulence onto the cockpit or the fuselage, all these external disturbances or vibrations are going to be accounted for. And now the enclosures that are kept inside the cockpit, all aviation electronic systems, avionics, has to be checked for sustainability. It should be stable, it should be durable, it should have a long fatigue life, and now there should be a proper tolerancing given onto the fittings, how these are bolted together, or say not bolted, I mean screwed together. And now each screw is going to experience, say let's say it's flying and it's trying to take off and the g force is increasing. Now it has become 2.5 g or say about 5 g at certain time. and then it has become 12G at some point of time. So there is a dynamic variation of G-force, and now all these G-force are going to contribute onto the screws. Every screw is connected to the modules, the electronic modules within the cockpit. Okay, so now those screws are supposed to be sustaining these G forces or the shock loads. So similarly, here there are going to be some shock loads or some kind of additional loads which is going to be generated, because we have given a pulse and we have given that pulse to find out, to check what is the kind of G force it is experiencing. Now we also need to find out whether the impeller is going to sustain that particular G force. So here in this case it is almost about 6.5 to 7G. Now this impeller is supposed to be sustaining that 7G. Now if the impeller is not able to sustain this 7G load, then again there should be an optimization or a design change done. We need to do some additional modifications. We need to brace it with some additional stiffeners, or we need to increase the thickness of certain members, the plates here, the top bottom stiffeners, or we need to look for an alternative option about reinforcing the collar. Okay, so we need to understand a lot of other things. Now let's study what are the other this one. So the equivalent power which is generated on the structure, so this is what we call the power density, radiated power density. Okay, now this will be the amount of energy which is dissipated, so which is almost about 0.5 watts per meter square. Okay, so now let's get into the next simulation, and this is going to have a relevancy in the next simulation, that is called the random vibrations, because this power density, whatever we see here, this will be the input data for the next random vibration simulation. This is called the power spectral density, and now we create a a pulse out of this. So this particular results what we see here, this is in terms of a pulse, excitation, super excitation, and these excitations are going to be the input data for the random vibrations, and this random vibration is what is going to decide whether the entire system is going to be stable, or whether it is going to have a higher fatigue life, and what kind of durability it has. So performing all kind of fatigue durability simulation, we do it from this. Acceleration. Okay, so now if this particular radial induced draft fan impeller weighing 0.7 tons capable of withstanding a 7.5 G force, that is what it means. So when I'll give you a small example about the cockpit of an aircraft. So whenever the electronic enclosures, the ECF, MC and ECU modules, electronic control units of the cockpit, whenever these modules are designed, they are going to be designed with a random vibration. They are going to experience certain thrust, inertia. So that can be about 1.5G, 2G, 3G, 5G, 10G, 12G. So it can go up to 15, 16 Gs. Now what is going to happen when it is above 16G? Whether the structure is going to wear out, because most of those enclosures are going to be fabricated systems, plates connected together, and they will be connected with the screws, and every vibration that comes onto the aircraft from the landing gear, okay, or even because of the turbulence onto the cockpit or the fuselage, all these external disturbances or vibrations are going to be accounted for. And now the enclosures that are kept inside the cockpit, all aviation electronic systems, avionics has to be checked for sustainability. It should be stable, it should be durable, it should have a long fatigue life, and now there should be, like a proper tolerancing given onto the fittings, how these are bolted together, or say not bolted, I mean screwed together. And now each screw is going to experience, say, let's say it's flying and it's trying to take off and the G force is increasing. Now it has become 2.5 G, or say about 5 G at certain time, and then it has become 12 G at some point of time. So there is a dynamic variation of G force, and now all these G force are going to contribute onto the screws. Every screw is connected to the modules, the electronic modules within the cockpit. Okay, so now those screws are supposed to be sustaining these G forces or the shock loads. So similarly, here there are going to be, some shock loads, or some kind of additional loads which is going to be generated, because we have given a pulse and we have given that pulse to find out, to check what is the kind of G force it is experiencing. Now we also need to find out whether the impeller is going to sustain that particular G force. So here in this case it is almost about 6.5 to 7 G. Now this impeller is supposed to be sustaining that 7 G. Now if the impeller is not able to sustain this 7 G load, then again there should be an optimization or a design change done. We need to do some additional modifications. We need to brace it with some additional stiffeners, or we need to increase the thickness of certain members, the plates here, the top bottom stiffeners, or we need to look for an alternative option about reinforcing the collar. Okay, so we need to understand a lot of other things. Now let's study what are the other this one. So the equivalent power which is generated on the structure, so this is what we call the power density, radiated power density. Okay, now this will be the amount of energy which is dissipated, so which is almost about 0.5 watts per meter square. Okay, so now I mean, let's get into the next simulation, and this is going to have a relevancy in the next simulation, that is called the random vibrations, because this power density, whatever we see here, this will be the input data for the next random vibration simulation. This is called the power spectral density, and now we create a pulse out of this. So this particular results what we see here, this is in terms of a pulse, excitation, super excitation, and these excitations are going to be the input data for the random vibrations, and this random vibration is what is going to decide whether the entire system is going to be stable, or whether it is going to have a higher fatigue life, and what kind of durability it has. So performing all kind of fatigue durability simulation, we do it from this. I also wanted to show the graphical outputs. So this is a particular scenario where the graphical representations are going to be more important. So now let's check. So this is going to be the central disk, and all across that central disk, let's see what is the displacement. So here you will find the displacement magnitude, the frequency versus displacement. The frequency versus displacement is what we see here. Okay. Now for that particular point, let's see what are the stresses. So this is the frequency versus von Mises stress. So frequency on the x-axis and the von Mises stress on the y-axis. So this is the stress plot, the frequency versus stress. Now let's see what is the magnitude of velocity. So this is the velocity plot. You have the frequency, so from 0 to 320. Okay, and our interest, the peak interest is about from this zone to this zone. So this is one region, so about 240 there is one, and then 320 there is one amplitude. So these are the two peak amplitudes. And then the acceleration plot, so this will be the acceleration plot. So now, yes, so we have, it is almost close to 9.5, okay, almost close to 9.5 meter per second square. So about 9.5 meter per second square. Yeah, it is almost our G value. 9.8 meter per second square is occurring at 240 hertz and then at 320 hertz. So these are the two excitation. Two times you will see that the system vibrates. And now let's see what is the power spectral density of the system. The power density. So this is the power density, and this is going to be the plot or the impulse that will be generating on the structure to find out whether it is going to be safer. And this is how the durability analysis or simulation is performed. Fatigue life can also be found, and then we have SN curve, different types of fatigue cycles, different formulations are there for predicting the fatigue life. And we also plot it, all the parameters put together, we'll be plotting it, which is called the rain flow matrix. So that we will see in detail in the next video. Okay, so here this is it. So we have seen how the model simulation is done, that is an actual frequency, and we have also seen how a forced simulation is done. So that is what we saw now, and how the frequency values are extracted, and to that frequency value how we are applying an impulsive load or an excitation. And once that excitation is given to the structure or applied on the structure, how does it behave? Okay, so with this, let me conclude the session, and the next session we will be dealing with random vibrations, how randomly the structure is going to be subjected to vibrations, and whether it is going to sustain, whether it's going to have an extended life, or what will be the life, how it will be, what will be the ratio, the damage ratio. Okay, so all these things will be seeing it in the next episode. So let me once again request you to kindly subscribe this channel and share it to as many people as possible, to your friends, engineers, or anybody who is working on these kind of structures. That will be a very interesting, this will be a very interesting video for them. They will be able to go through the entire, the simulation cycle. So starting from the basic stress analysis to model dynamics and frequency response, dynamic vibrations, the random vibrations, everything will be covered of a single product. So here it's the draft fan radial impeller, for which there is some boundary conditions and loading patterns, and how does it respond, and what will be the durability. All those things that will be focusing on the next. Okay, so please subscribe and share, and feel free to send your valuable comments, queries will be answered, and you can also request if you are interested to have a group, and we can work on a group, we can have interactions, make it more interactive. Okay, thank you.